You take your attendance. Yeah, so let's start our lesson today. I think 17 of you, yeah. Okay, so let's cover up the nuclear. Okay, nuclear physics. So that's the 13th topic, right? Okay, so recall back what we learned last class. Last class we started the topic. Okay, so yeah, so nuclear physics. So we talked about the mass defect and binding energy last class. Okay, yesterday. We will be doing maybe for 10 minutes, strengthening the idea of binding energy. Then we move on to radioactivity. Okay. Okay. So first we learned about what we learned last class. We learned about mass defect. Okay. When the nucleus is formed, the mass found to be different. The total number of nucleon is the mass of the total number of nucleon involved in the formation of the nucleus is found to be different than the mass of the nucleus. Okay. Normally, the mass of the nucleus is getting lesser. Okay, it's lesser. Okay. So yeah, mass change. The change in mass in the nuclear reaction is said to be change tend to become energy. Okay. If the changes in mass is increases, means what? Very rare. The first one happens. Okay. The one I focused last class was the mass is decreased. Okay. The second one. So let's be focused with the second one first. If the mass is decreased in the nuclear reaction, that means product has less mass than the reactant, then energy will be released. Okay, energy will be released. The energy release we calculate by using mc squared. Okay, so normally the naturally occurring process, all are the mass is reduced. Okay, when uranium was blast with neutron, convert to strontium and other substance, the mass of the daughter nucleus, all the products together found to be less mass compared to the reactant. Okay, mass reduced. Okay, there is some man-made nuclear reaction also. Man-made, the mass was increased. Okay, mass was increased. That means the product found to be more massive than the reactant, the nuclear reaction. Okay, so in that case, energy need to be supplied. Okay, energy will be absorbed. Okay, so we will discuss about that mass increase later. First, we focus to the mass decrease. Okay, the normal acting reaction. Okay, then we talk about what is meant by unified atomic mass. Recall back, so 1/12 of the mass of the carbon-12 atom. The definition. Then we talk about binding energy. What is binding energy? the amount of energy required, yeah, to remove all the nucleons from the nucleus so that they are completely separated to infinity, the binding energy. Okay. If a nucleus has a very high binding energy per nucleon means we say more stable. Yeah. This is the graph I told you. Iron found to be the most stable nucleus. And we talked about fission and fusion. Okay, in the nuclear process, a lot of physical quantities are conserved. Okay, you know this earlier in your AS. Okay, these here few are listed. Of course, charge is conserved, total nuclear number is conserved. Something new we're going to highlight here a lot. Of course, the third one, conservation of mass and energy. Mass and energy together is conserved. And a lot of things are conserved. If you go further studies in your maybe in you take in universities, let's say you tend to do physics, let's say, you will see about 7 quantities are conserved, a lot. But we can add another one here, the one conserved. What is that? Another one conserved? The one, linear momentum, right? Linear momentum is conserved. Of course, linear momentum is conserved. Okay. So this for A levels, conservation. Okay. So I go to the whiteboard. I just want to restate this. Okay, what I want to restate, let's say a neutron was bombarded with uranium. It forms a 2 daughter nucleus, X and Y, okay, and release gamma ray, let's say, releases gamma ray. So let's say the energy is found to be negative 200, let's say, mega eV. It's negative. Negative shows that it's an exothermic process. It's an exothermic. Exothermic means, if exothermic means XY is found to be more stable. Of course, XY is more stable if it's exothermic. Yeah. Yeah. So another thing I want you to remember is what is greater for X and Y? For X and Y, for the case of X and Y is more stable than uranium, of course. Which have a greater binding energy per nucleon? X and Y will have a greater binding energy per nucleon, for sure. Okay. And third, okay, this I never mentioned this last class. Okay. So which will it be more massive? If the reactant will be more massive, the total mass of the reactant, is more massive, or the total mass of the product will be more massive? Which will be more? Which will be more massive? The mass of the reactant will be greater than the mass of the product. Okay. So mass will decrease. The mass will decrease. Okay. So for that, it's an exothermic. If it's an exothermic process, mass should decrease, releases energy. Okay. So more stable compound will be produced. And the fourth one also I never mentioned last class. Okay. Binding energy per nucleon for each product is higher than the binding energy of the reactant. No doubt about that. Okay. But remember the total. But total binding energy, the total binding energy of product, okay, is greater than the total binding energy of the reactant. Okay. Okay. So the last two is just I'm going to this is something new addition. So when the process they found energy is released, that means you should know the product is more stable. Okay, you should know binding energy per nucleon of product is greater because more stable. You should know because it's an exothermic, the total, this is the total, and the total mass of the reactant must be greater than the total mass of the product. The total mass of the product. Okay. And finally, You should know the total binding energy of the product should be higher than the total binding energy of the reactant. Please include this in your notes, something like a summary. Okay, this only happens for exothermic process, if nuclear process is exothermic. Okay, any questions from here? No questions, Okay. So let's move on from here. We go to the slide. Okay, that day we discussed about fission and fusion. Okay, let's go one example. Okay, this is one example. We want to calculate the energy release for this process. Okay, look at the question. Let me check. Am I recording? It's important. Yeah, it's recording. Yeah. Okay. Okay, look at the question. One nuclear reaction that could occur when the nucleus absorbs a slow neutron is this. This is a nuclear fission. It's a nuclear fission. Uranium was bombarded with neutron as usual, and it got the product. Okay. So now you see the details. The binding energy per nucleon for each of the product is given by this. Okay, they give binding energy for each of the reactant and product. The uranium binding energy per nucleon found to be 7.59. The binding energy for La, one of the daughter nucleus, is found to be 8.41 mega eV. Of course, greater binding energy per nucleon, more stable. Product is more stable, right? When energy released, naturally occurring process. Binding energy per nucleon for bromine Br is found to be 8.59. Okay, this is binding energy per nucleon. Okay. Okay, first identify what is the element and X and Y can be. Can you tell what is X, what is Y? Use your nuclear knowledge. Figure out what is X and Y could be. So 146, 87. So at the bottom is 57, 35. Here should be 92, right? Should be 92. So 57 plus 35, how much? It's also 92. It's also 92. That means X should be at the bottom, both must have a 0 proton, right? Must have a 0 proton number. Okay. Go to the nuclear number. Nuclear number 146 plus 87. Is it same as 236? Check how much. 146 plus 37. What do you get? 146, 146 plus 87. So you got 233. You got 233. So these two add up. The nuclear number is found to be 233. So you got 236. So of course, because 3 here, so it should be 1 lah, right? On top should be 1. You put 1. So 1 0 lah. It's of course it's neutron. X is neutron. 1 0. 3 neutron was released. Then Y should be 0 0. What is 0 0? Most probably is a type of radiation lah. It's gamma ray maybe. So gamma ray was released. Yeah. So X is neutron. And Y is gamma ray. Should be gamma ray 001. Gamma ray is released. Okay. Those who got X is neutron and Y is gamma ray. Good. Okay, A2. Name this type of nuclear reaction. Of course, this is nuclear fission. It's a fission, right? It's a fission. Okay. Okay, look at third part, part 3. Okay, explain why neutrons are used to split uranium. I believe you learned this in your early studies, right? Why they never use proton? Why they never use electron to split the uranium? Why they use neutron? Of course, because it's neutral, right? Okay, because it's neutral. So because neutron is neutral, so easily can enter into the nucleus without any repulsive force. Okay, that's why neutron is used. Okay. So next, so I expected 1, 2, 3. Part A you should know before without my input. Okay. Okay, look at part B. Okay, this is your turn now. I give you 2 minutes. Figure out. Estimate the amount of energy released in this process. Okay. How much of energy released in this process? Okay, how are you going to get energy? Okay, so this is what something new you're going to learn. Okay, you see here, they never give individual mass of the particle, They never give the individual mass of the particle. If they give individual mass of the particle, like uranium, in this case, they put 235. If they put 235 with the 6 decimal places, then we can find the mass defect, the mass differences, and we use mc squared to calculate the energy. But in this case, the mass of the each particle is not provided, okay, for 6 decimal places. Okay, of course, no decimal places is given, 235, but we want 6 decimal places because the mass is going to change very little. We only can see that when we go for 6 decimal places. So using mc squared is difficult. We don't know the mass for 6 decimal places. But what is given is the binding energy is given. Binding energy per nucleon for each element is given. Okay. So remember, guys, when binding energy per nucleon is given, energy you need to calculate, the energy release need to calculate by using this binding energy. Okay. So what you have to do is find the total binding energy differences. Okay. So I clear this. You see, find the total binding energy of the reactant. Find the total binding energy of the reactant first. Okay. Then find the total binding energy of the product. Okay. So what I told you earlier, the total binding energy of the reactant greater or product greater. Let's say this is like fission word. It's a fission process. Of course, energy is released. Okay. So energy is released. If energy is released, total binding energy of reactant greater or product greater? Which binding energy is greater? Just now I told you. The product has a greater binding energy. The total binding energy. I mean, the total binding energy of the product will be greater than the total binding energy of the reactant. If it's an exothermic, if energy is released. Okay. So remember that. So when energy is released, the total binding energy of the product is greater than the total binding energy of the reactant. Okay. The differences, the differences in the total binding energy of the product minus the total binding energy of the reactant is the energy release. Is the energy release. That's the energy release, which last time we calculate by using mc squared. Okay. So the energy release, now you get to know there are 2 ways you can calculate the energy release. One by using mc squared, if you know the mass for 6 decimal places, or you get the binding energy per nucleon. Find the total binding energy of the product minus the total binding energy of the reactant. Okay. Okay, now first, let's see. How do you find total binding energy of the product? How many products are there? There are 4 products, right? Got La, Br, neutron, and gamma. Okay. So remember, the neutron and gamma don't have any binding energy. In exam, they will ask, why neutron don't have binding energy? Why neutron and gamma don't have binding energy? Because it doesn't bind with anything. It's a one single particle. Okay, one single particle don't possess any binding energy because it doesn't bind with anything. It's a single particle. So in exam they ask why the neutron don't have binding energy. You say it's a single particle. So therefore you don't have binding energy. Okay, so the total binding energy, I made a mistake here. Uranium plus neutron, right? I told you that's the reactant, but uranium, yeah, the intermediate I don't want to use. This is the product. The La, Br, X, and Y is the product. Okay. So the binding energy of the product is only contributed by the daughter nucleus, the La and the Br only. Okay. This is the total binding energy of the product. Neutron, gamma doesn't contribute any binding energy. Okay, clear? Huh? So for La, how much is the binding energy of La? You know binding energy per nucleon of La is 8.41. So what is the total binding energy of La? So just 8.41 multiplied by the nucleon number. Okay. So the 146 multiplied by 8.41 will give you the binding energy of the La. Okay. Then plus with binding energy of the Br. Okay. So like this is the working. Okay. So look at the B. We find the binding energy of the product. This is the product binding energy of the product. Total binding of the product. La plus Br. So 146, the nucleon number, multiply the binding energy per nucleon. This is the binding energy of La. And for Br also 87 times 8.59. This is the binding energy of the Br. So the total binding energy of the product is found to be 1975.19 mega eV. Okay, this is the binding energy. This is the total binding energy of the product. Okay. So we do the same thing for binding energy for the reactant. In this case, we got two members in the reactant, right? Who's that? Neutron and uranium. Okay. But yeah, they give binding energy of the 236 uranium. So we use 236 uranium. Yeah, so the binding energy of the reactant is only contributed by the 236 uranium. So 236 times 7.59 will give the binding. This is the total binding energy of the reactant. Okay. Yeah. So remember a new idea. The amount of energy release is actually the total. This is actually what? The total binding energy of the proton product minus the reactant is the energy release. So 184 mega eV of energy should be released in this process. Okay. So this is another way of finding energy release by using binding energy. Okay. So if it's an exothermic process, if its energy is released, that means total binding energy of the product is greater than the total binding energy of the reactant. So the total binding energy of the product minus the reactant is the energy release. Okay, guys, very important. I hope you got the idea. Okay. So in exam, remember when they give binding energy per nucleon, find the total binding energy of the product, total binding of the reactant, minus them. That's your energy release. And this energy release, if the question asks what is the mass defect for this process, from this energy release, we just equate with mc squared. We can find the mass defect if they ask my mass defect. Okay, from backdoor actually to find the mass defect. Okay. Okay. Any questions? Okay. So now the energy release, see, suggests how energy released during this nuclear reaction, suggests how energy is released. The energy is released in what form actually? The energy release is actually will be the kinetic energy of the product, all the product. The energy release will be in form of the kinetic energy of the all product, which towards the end will turn up as an heat energy. Okay, the internal energy of the substance rise turn to become heat energy. So the originally what happened? The energy is released as a energetic photon and the kinetic energy of the all the products of La, Br, and neutron all going to move away. Then later they appears as a heat. You know, right? This is what happened in the nuclear reactor, right? Okay. The nuclear energy will convert to kinetic energy of the product and turn to become heat. The heat will vaporize the water. The water vapor steam will channel to the turbine. Then we generate electricity. Okay. So you know, nuclear reactor produces heat, but before heat, how the energy was transferred as a kinetic energy of the products. Okay, of the products of the reaction. Okay. Okay. So hope you got the idea. Eh? Okay, now let's see go. Another type of question, calculating the energy. Another type of question is this. Well, this one is suggests attain temperature. This is not that important. We skip this first. Another type of question is another type of question is the earlier questions. Sometimes they give mass, like before this. Yeah, this question, the earlier one. Two proton neutron become helium. So what is the energy release? So you find the total energy of the total mass of the reactant minus the total mass of the product. You get the mass defect and use MC squared to find the energy release. Okay. Okay, class. So conclusion is when they give uranium react gives you X, Y, whatever. Okay. If they give binding energy per nucleon, the total binding energy of the product minus total binding of the reactant will give you the energy release. Okay. Okay. Sometimes if they give mass for 6 decimal places. If they give mass given, then what do you have to do? Find the mass defects, of course. So how do you find the mass defect? Mass defect is which mass is greater? When come to mass, the reactant will possess a greater mass. So the mass of the reactant, the total mass. When come to mass, the mass of the neutron all will be included. The mass, because mass, every particle has mass. Right? So when you come to find the mass defect, if let's say reactant got neutron and uranium, the both masses need to be included. So that's the total mass, reactant mass, minus the total mass of the product, X, Y, plus if you got neutron mass all included, mass of the product, times C squared, get the energy release. Can you see the difference here? By using the binding energy, to find the energy release is total binding energy of the product minus the total binding energy of the reactant. Okay. When calculating the energy release by using the mass, total mass of the reactant minus the mass of the product. Okay, you get the mass defect, you can find the energy release. Okay. Okay, guys, so hope you got the idea. Okay, any questions so far? No questions. Okay, so this consider the part A of this topic. Okay. So now this question is okay. I go to the next part. Okay, the next part we're going to discuss is radioactivity. Okay. Okay, this is the part B. Okay. So this is a very short part. We talk about half-life and anything about half-life, and we'll be introduced with a new formula for half-life. Okay, recall back. What is radioactivity? You learn in AS, right? What is radioactivity? It's a spontaneous and a random process, right? Experienced by a heavy unstable nucleus into more stable product, okay, by emitting energetic radiations. Okay, keyword is what? It's a type of process, a spontaneous and random process where an unstable, heavy unstable nucleus. This is important keyword. One mark. And very unstable nucleus turn to become stable product. One mark. These two are one mark. Unstable becomes stable. One mark. By emitting energetic radiation. Emission of radiations. One mark. Okay. Radioactive decay. So you learned this in your AS, right? Just recall back. Okay. So why the process is spontaneous? Why the process is random? We discussed in AS, right? Why the radioactive process is spontaneous? Why the radioactive process is spontaneous? Because it's unaffected by what? It's unaffected by external factors. Unaffected by external factors. such as pressure and temperature. So that's why radioactive decay we consider spontaneous. The process is spontaneous. Okay. Why the process is random? Why the radioactive process is random? Because we don't know how many atom and which atom will disintegrate at a particular time. It's totally random. Okay. Maybe the first time, maybe the on surface 5,000 surface atom nucleus will disintegrate. The second, maybe the inner uh, uh, nucleus will be disintegrate. We don't know. It's totally random, unpredictable. Okay. So now let's we go in depth about calculation part. Okay. This is a useful setup. If a design experiment comes out something to do with radioactivity, how do you take radioactivity of a source? What instrument do you use? Use a GM tube. We use a GM tube, Geiger-Müller tube, connected to a something called rate meter. Okay. So last time I think your O level maybe you know only GM tube, but A levels you have said GM tube connected to a rate meter. Okay, so count rate meter. So the GM tube connected to a rate meter measures the activity. Okay. Okay. So now we are going into a formula. Okay, now before we go to this formula, I want to ask you one question. Okay. Okay, let's say you have uranium, 1 gram of uranium, a small dust, one small speck of uranium, and you have 1 kilogram of uranium. Okay, so both are uranium. Okay, you place GM tube the same distance away from these two source. The GM tube reading, the count rate, is it going to be same or different? Is it going to be same or different? 1 gram of uranium, 1 kilogram of uranium, same GM tube. Okay, GM tube use. The count rate, is it going to be same or different? Definitely different, right? Okay, the 1 kilogram of uranium will have a greater count rate reading. The activity is greater. Okay, so the activity, we call it activity lah. We call activity. How many disintegration happens in a second? The activity of the source is directly proportional to what factor from this observation. The activity is directly proportional to, looks like the mass, right? 1 gram greater the mass of the what do you call the radiative source, greater the activity. So instead we say mass, we say more in depth the number of particle contains in the radioactive source. So the activity is found to be proportional to the number of atom of the radioactive source available. Okay, this is the fundamental proportionality which used to develop 3 main formulas in radioactivity, which including the half-life formula, all based on this proportionality. Activity of a radioactive substance is proportional to number of particles. Okay, there are 3 formulas to be developed. Okay, so we go back here. So yeah, so that's what it has been discussed here. The DNDT is actually activity. This is your activity. The number of particle disintegrate per unit time. Activity. It's negative because it's always decay. It's always decay. That's why it's negative. So DNDT proportional to n. You can say activity is proportional to n. Okay. So the activity, when we equate, we bring a constant. So in this case, the constant is labeled as lambda. Put lambda. Okay. So activity is negative lambda n, but your A levels, the negative, they just omitted. It's not included in negative. They just call the lambda as a decay. That's it. Because they say call it as a decay, the negative is not included. So the formula will be used in your Cambridge is just without the negative. So activity just lambda n. Okay, so A equals to lambda n, the first formula for activity, okay, radioactivity. A stands for what? Activity. Lambda is called a special name called decay constant. Okay, the lambda is as a special name called decay constant, and n is the number of particle, of course, number of nucleus. Okay, number of nucleus or number of particle in that radioactive source. Okay, so now this is something new. Now the decay constant is a very important definition. Like, you know, quantum physics, photon is a major definition they will ask. So for a nuclear, for radioactivity, the decay constant is the famous definition they're going to ask. Okay, so what is meant by decay constant? Okay, I don't want you to take this definition. There is another one definition for you to write. You take this definition, the other one. The other one is better. Easy to understand. Okay, so we go back to the word file here. So this is the decay constant definition. Please include this. This is the definition for decay constant. What is decay constant? The probability that an individual nucleus will decay per unit time. That is decay constant. Please remember this. First question in the structured question for a nucleus, it comes out. Most probably the first question they will ask is define decay constant. Okay. So what is decay constant? It's a probability. It's actually a probability. Probability for an individual nucleus to decay per unit time. That's decay constant. Okay. For example, let's say you have uranium. They said uranium has a decay constant of 0.5 per second. So what do you understand by this? What do you understand by this is if every nucleus in that uranium, has a a probability. It has a probability of 0.5 to decay every second, every moment. Every moment, every nucleus has a 50%, right? Like a 50% possibility to decay. Okay. So conclusion is, I don't know how well you understand this. If a substance, you have a substance A, you have a substance B, two substance. Substance A has a lambda A, substance B has a lambda B. Okay. Let's say substance lambda A is greater than lambda B. Lambda A is greater than lambda B. Okay. Can you tell which substance is highly radioactive, highly unstable? A or B? Lambda A is greater than lambda B. Look at the definition for decay constant. Figure out which is very unstable. Anyone? Nisha here? Nisha, what do you think? Lambda A or lambda B? Which is more unstable? Nisha not here. Okay. Angus, what do you think?
A, sir.
A, yeah, for sure. A, right? So greater the decay constant, remember, greater the decay constant, more unstable the element. Okay. So the maximum lambda can go is, of course, probability maximum value is what? 1, right? We don't have anything like decay constant of 1. If you have a substance with a decay constant 1, means it has a probability to decay, 100% probability to decay per second. That means if you have a substance with a decay constant 1, means that substance immediately going to disappear from the surface of the earth immediately, because you're going to disintegrate immediately. So lambda decay constant is always less than 1, the lambda value. Okay, more greater the magnitude, more unstable the element. Okay. Okay, so we go back. Okay. So yeah, so activity equals to lambda n. So greater the lambda, so more unstable the element. Okay. What is the unit for lambda? Per second. Can be per second, can be per minute, can be per day, can be per year. Okay, got lots of unit for time, right? But if you use this formula, A equals to lambda n to calculate the activity, the lambda must be in per second. Okay, please remember, if you use A equals to lambda n, lambda unit must be in per second. Okay, if the question give purposely, they give per minute, they said 0.2 per minute is the lambda, and you want to use this formula to calculate the activity, the lambda you have to convert to per second. Okay, how do you convert to per second? 0.2 per minute, how many per second? So 0.2 divided by 60, right? 60, so you get in per second. Okay, so then only you can use lambda here. Lambda have to be per second. Okay, good. So this is the first equation. Okay, so how this formula can be used? In exam, how this formula A equals lambda n can be used? They will tell you there is 20,000 particle of uranium is contains in this substance, and the activity is found to be 50,000 becquerel. Yeah, the unit for activity is becquerel, or yeah, we call it as a becquerel. What is becquerel means? 50,000 becquerel means we said 50,000 disintegration happens per second. Yeah, that means 50,000 what do you call? 50,000 nucleus disintegrate at a particular time. Okay, so that's becquerel. I'll come back to this unit later. Activity is becquerel actually. So they will tell you 20,000 particle as activity of 50,000 becquerel. If the uranium has 100,000 particle, what is the activity for this will be? So of course use A equals to lambda n. Okay, because both are made of the same substance, lambda is the same. So A over n for the first one should be same as A over n for the second one. So you can find the activity, the new activity. Okay, so first equation, okay, used to find activity for specific number of particles. But this is not the famous formula. The famous is the next formula, a very famous one. Under these three formulas, this second one is the most famous. Okay, the second formula will be introduced is the last one here. Okay, this is the second formula. Okay, the derivation you no need to know. It's not in your syllabus, but you need to know how to use this formula. Okay, actually, this second formula is obtained from the first formula. A equals to negative lambda n. They bring the n to the other side, dt the other side. They integrate it from n and naught. N and naught is the number of particles still remain. N naught is the original particle. N is the number of particles still remain after of time t. Okay, after of time t, right? When a substance allowed to decay, the number of particles will reduce, right? Will change to other substance. Okay, so they put the limit of n and n naught. You know, integration is done. Finally, they got this formula. Okay, so the derivation just for your understanding, but you need to know the final formula. The final formula is what? General formula is x equals to x naught e negative lambda t. Okay, second formula. Okay, this formula let's understand in depth. The x is actually representing, according to the derivation, is the n. The n is what? Important. The n here is the number of particles still remain. Remember, important. The n is what? The number of particles still remain after of time t. Okay, let's say you have 1 million of particle after time t, only 300,000 left. Okay, so the n is 300,000 t after a certain time. Okay, the x naught is n naught, the original number of particle when the time zero. When the zero time, what is the number of particle it possesses? That's n naught. Okay, so E is exponential, lambda is decay constant. This is how they related. Okay. And this formula, why they wrote in a common formula is not only for a substance, for a substance, the n will decreases exponentially. The number of particles, not only n decreases exponentially, the activity decreases exponentially. The count rate decreases exponentially. The mass of the particle, the total mass of the uranium or of the radioactive substance decreases exponentially. So four quantities will decrease exponentially. Okay. So in exam, they won't ask you to calculate, find the number of particles after 2 hours later. So if they ask find the number of particles, the formula is n equals to n naught lah, in terms of n. Okay. But they can ask you, what is the mass of the uranium still left after two hours later? They can ask mass. So for mass, the formula change, the n change to m. You can change to m equals to m naught e negative lambda t. You can change to m. Okay. They can ask count rate. They can tell. Okay, the original count rate when the time 0 is 20,000. After two hours later, what is the new count rate? Then use C equals to C naught E negative lambda T, which is the X replaced with C, and so on. Okay. So this four quantity can be decreases exponentially. Okay. Second formula. Okay, this is the most important formula. And when you use this formula, important, the lambda T, right? The lambda and T must be the time unit must be the same unit. What I'm trying to say. So n equals to n naught e negative lambda t. Okay, lambda given per minute. Okay, lambda was given in per minute. The time you want to find what is the activity after 60 seconds. Okay, I'm asking what is the number of particles still remain after 60 seconds. So you find the n, the original n naught you put e, the lambda, let's say in per minute, let's say it's per minute, the time also have to be in minute. Okay, that's the trap here, common trap. The lambda t, the time unit must be the same. If lambda is per minute, time must be in minute. Okay, if lambda is per year, then time also you have to put in years. Okay, don't mix up. Okay, one convenient here is the lambda you can use any unit you like. Okay, not like a equals to lambda n. A equals to lambda n, lambda have to be in per second. Okay, if you use lambda t, the lambda you can use any unit you like. You can use per year if you want. If the question give per year, the lambda they give per year, 5 per year. So the t you have to put in years lah. That's all. Okay. So hope you got the idea. Okay, second formula. Okay. So the A, as I told you, is actually the activity. Activity is the unit is becquerel. 1 becquerel means 1 disintegration per second. That means one nucleus or one atom radiate to become daughter nucleus. 1 becquerel means this is the SI unit for activity, becquerel. Okay. Okay. So I believe you learned this formula, right? For half-life. So when n naught for first half-life, the n naught become half n naught, second half-life become quarter n naught, and so on, right? This is like every half-life, the n naught reduced by half, correct? Yeah. Okay. So this n is the radiative substance which is still remain, still remain. Okay, let's say uranium. The n is the number of particle of uranium still remain after time. This graph drops exponentially. The formula now you know n equals to n naught e negative lambda t. O level you never learned, but now the graph is drops exponentially. This is the formula. Okay. Okay. So now the last equation to be introduced is about half-life. Okay, you well versed about half-life. Okay, so what is half-life? Okay, the time taken for a number of radioactive nuclei to disintegrate to half of its initial value. Okay, okay, class. Again, here very important keyword is missing. Yeah, average time. Okay, please include half-life of radioactive nuclei is the average time taken for the number of radioactive nuclei to disintegrate to half of its initial value. It's average time. Why average time? In reality, the n versus time, you know, right? It's a random process. So the n not going to drop smoothly, right? You're going to drop how? You're going to drop like this, up and down, up and down. So the half-life is actually the average time. It's the average time for the number of particles to decay to half of its original value. Okay, it's average time. Okay. So far I told you the first derivation of the first two equations you don't need to know, but these derivations is in your syllabus. You have to know this derivation, the derivation for half-life. Okay. The half-life formula they discovered is how? By using the second formula. N equals to N naught E negative lambda T. When the time is half-life, the N will be N naught over 2, right? Right? And the time is half-life. The N remain is N naught over 2, half of the original number of particles, correct? So we substitute the T as T half and N is N naught over 2. Yeah, so that's all. From here, cancel the 2. Cancel the N naught. Is 2E negative lambda E lambda T half. Actually, this is actually half E negative lambda T half. So I make it here 2, then the power here become positive lambda T half, right? Your maths indices. So bring ln both sides, become ln 2 lambda T half. So make the T half as a subject. This is the formula for half-life. For the first time, you have a formula for half-life. Okay. The half-life of a substance is actually ln 2 over lambda. Okay. Or ln 2 is actually 0.693 over lambda. Yeah. So this is the third formula. Half-life is found to be inversely proportional to the lambda. Okay. Greater the decay constant, smaller the half-life. Makes sense, right? Greater the decay constant means very stable or very unstable the substance. Which substance has a greater decay constant? Very unstable substance, right? So very unstable substance most likely to disintegrate fast. So you'll have a very short half-life. You'll have a very short half-life. Yeah. So half-life is inversely proportional to the decay constant, proven from this equation. Okay. So this third formula, you can use lambda any unit you like. Half-life also you can use any unit like. No need to be SI. If lambda you use per year, then the time will be in year. Okay, if half-life if lambda is in per minute, your time will be in minute. Okay. Okay, good. So that's the last part for today. Just introduction of 3 formula about radioactivity. Okay, I stop here. So what you learned today? Radioactivity. The activity is found to be proportional to number of particles, which leads to lambda n. Okay, the lambda is called what? Decay constant. Okay, what is decay constant? Probability. Okay, it's a probability for an atom to decay per unit time. Okay, per unit time. Okay, unit is per second. First formula. Second formula, n equals to n naught E negative lambda T. Second formula. Okay. Second formula, the n is the particle still remain. Okay, I'm highlighting this many times because this is a common mistake students do. The n is the one still remain. Okay, the particles still remain. Okay, So when you use second formula, make sure these two are same unit in terms of time lah. If time is minute, lambda must be per minute. Okay. Okay, then the third formula now, the derivations you have to know, we use it from the second one. Okay, so when t is t of n will be n naught over 2, right? N naught over 2. So n naught over 2 equals to n naught e negative lambda t of. Okay, rearrange this, bring the ln both sides. So we found half-life is ln 2 over lambda. Okay, so this is the third formula in your list. Okay, now the questions they're going to ask by using these three formulas. Okay, these are the three formulas. Okay, class. So next class we'll be discussing how these formulas has been used. Okay, I catch up with you on Monday. Okay, any questions so far? Anybody? No questions. Okay. So those who have questions can stay back. Those who don't have can leave. Thanks.